Hello interwebs, welcome to Let's Fix Computers. Got another MacBook Air here, A1466, doesn't turn on. So let's have a look. I have already removed the back cover of this. I wanted to do a sneaky inspection just to see what was going to be going on with this. And the moment I saw the inside, I was like, Mom, get the camera! So, yeah, I thought it was definitely interesting enough to be worth putting on film. So, it's super gross in here. But the bit that started catching my eye was that it's going rusty, everyone. It's going rusty inside. So this thing has obviously seen liquid, and man, it's a hot mess in here. It's not beyond saving, but we've got various bits of corrosion around CPU V-core here, and the whole thing is really dusty and grossy and a bit horrid. So let's roll the intro and take a closer look at it. So, firstly, let's roll back a little bit and take a look at our dust patterns. I always look at dust patterns. So, we've got a lot of dust, lots of grot. So, remember, a bit of light dusting is completely normal and okay. I call it honest dust, you know, just because every laptop gets dusty. It's normal. However, there's also just a lot of just dust and fluff buildup, and that can start turning into a problem because it accumulates moisture and holds moisture in the laptop, which is bad. And we've got a couple of spots around here that look like tide marks where there's been some liquid in here. And that tallies with this rust patch we're seeing down here. So I definitely think there's been some drops of water in here at some point. We don't know what the back looks like. But maybe this has had a light splash at some point. Doesn't look like a disaster case, but it's there. So I'm going to get the battery disconnected, and as usual, as soon as we see any kind of corrosion on the board at any point, the board has to come out, because we don't, you know, we could start looking at this, we could start taking measurements, but we have to see what the back of the board looks like, because it might be a disaster case on the back. So I'm going to start stripping this down now. So let's go fast forward mode, get this logic board out. Oh boy. Oh, and that, everyone, that's why we look at the back. Yeah, this thing got flooded out. Probably is spilled directly on the keyboard, since the worst of it is on the back. Yeah, like why is there a feather there? What happened? There are a couple of philosophies when faced with a situation like this. It might be savable, but a lot of people are very much of the opinion that once you've had liquid damage, especially liquid damage to this extent, the board is doomed. Even if you get the board working again, even if you fix it and it works, it's probably going to die again in the future. Now, personally, I'm willing to roll those dice. I'm willing to run the risk on that. I will usually advise the customer and say, you know, look, this thing was pretty badly damaged. We've got it working, but, you know, I would expect to see problems with this in the future, because that kind of damage, you never really fix it, you know. And, you know, if it's, I will provide a warranty on it. By and large, I've not had a lot of repeat failures. I have seen laptops that have come back in again later on, but this has been a long time down the line, like a year plus down the line. And I think paying for the repair to get like another year out the laptop isn't unreasonable. The other thing to consider as well, though, is this is a 1.4 gigahertz 4GB model. You know, this is not a great logic board. And another line of thought would be to just replace this logic board and put in a stronger one. Like this, I think this is going to be a 3437. Hang on a minute. Yeah, this is an 820 3437. We can drop an 820 00165 in here. This is like a 2015 board, I think it is. And the 820 00165 is the 2017 board. And this chassis, they didn't change this chassis for years, so you can just drop a 1.8 gigahertz, 8 gigabyte RAM logic board into this laptop and just modernize it. And the 00165 board, you can find those on eBay for less than £100. So if we put things into perspective, if I were doing a board repair on an old MacBook Air like this, I'm looking to charge somewhere between £80 and £100 for the board repair. And like, you can buy a replacement logic board for that kind of money. But if we're looking at this from the customer and the shop perspective, you might say, well, okay, if you can buy just new parts for the same amount of money as the repair, why wouldn't you do that? Well, if I spend 90 quid on a new logic board, that's £90 that we've spent fixing the laptop, and at the moment I have no profit. So if I want to make any profit on that, I've got to charge labour on that as well. So we say, what are we going to charge for fitting? You know, £50, £60, you know. So we're now talking £150 to fix the laptop. If I could fix this motherboard and do it on the cheap because it's an old one and say charge 80 quid for it, I've now done half the repair bill to the customer and I've doubled my profit because I'm making 80 quid. Well, not quite doubled, but I'm making 80 quid pure profit instead of like £50 or £60 profit. And I've done it cheaper to the customer. So that's why we bother fixing the boards, because it's a higher profit margin and a lower cost to the customer. Everybody wins. But in this instance, you have to consider what the value proposition is. Even though you're giving the customer a potentially lower bill, are they getting a better value proposition? I'm not so sure. So I think what we're going to do is, for the sake of, if I wasn't making a video about this laptop, I think what I would do is probably push the customer in the direction of a replacement logic board, because I think that's going to be a better value proposition. But for the sake of the video, we're going to try and fix this anyway. And then I may end up saying to the customer, I did get your board working, but I don't fancy its chances. We should replace it. So this is potentially going to be a waste of my time, but good for education and good for practice. The other thing as well is there's a very good chance that this thing is just shot to hell and just don't even bother kind of thing. So let's take a look at this and see what we can do about this and just see where this goes. It's worth noting that because this is an older MacBook Air, the SSD is removable, so we don't need to worry about data recovery here. These SSDs are conformally coated. They're pretty damn rugged, these things. They are not immune to failure, but like there's not a mark on this thing. So we could plug this into another logic board, even another MacBook laptop of the same era, and that'll just boot up with the customer's data on it just fine. So we are doing this purely to save the hardware. We don't need to worry about trying to preserve any data or anything like that. So let's move this chassis to one side. Under the microscope, you can see the extent of the damage we're dealing with here, and this is kind of the problem. There's so much rot on this. Like there's so much just tarnishing and just corrosion where it's literally just eaten into the board. You can see where the dust has just held on to that moisture as well. This looks like old damage to me. I don't think this is recent. You know, I think this probably had a liquid spill quite a while back. It got, oh man, it's horrid. Let's come off of the microscope. You guys have seen enough. Stop, it's already dead. Yeah, so I think this is probably old damage, and it's just continued to eat away to the board, and something has given up at this point. So where do you even start with this? Well, for me, if you've got a small amount of corrosion on a board, I usually say start taking measurements so you can see what the problem is. You know, don't erase your clues and stuff like that. But when you have this extent of damage, the only way to start with this, I think, is to do a very quick visual inspection and go, okay, we had corrosion on these areas, and then just start by just doing a complete clean of the board. So you can either do that just by covering it in alcohol and toothbrushing the board down, or in my case, I'm probably going to lob this in my ultrasonic cleaner and just see what happens. we can just see what that makes of it and what we get out of it, and try our luck. Then if it doesn't work after the ultrasonic cleaner, it will be cleaned up, and then we start going over it and doing our diagnostics. My ultrasonic is made by Vivor. It's a big 20-litre unit that was generously purchased by one of my Patreons. I have distilled water and a generic flux cleaner ultrasonic solution in there. I run it at 50 degrees C for 2 minutes per side, then I drip dry the board, followed by an alcohol spray, which I then blow dry with compressed air to chase any residue out from under VGA chips. Well, folks, the ultrasonic cleaner has done its work, and if I say so myself, it's done a stunning job on this as well. I think a lot of that stuff maybe wasn't quite as ingrained as it initially looked. A lot of it really was just surface level. If we flip the board over, as you can see, it looks like it came out of the factory yesterday, to be honest. Now, if we take a closer look under the microscope, we'll see that it's not all sunshine and roses. However, having looked at this thing after cleaning it up, I'm thinking, you know what, maybe this thing will survive after all. So if we look at the SMC here, this area was looking particularly nasty, and as you can see, that is sparkling. You know, there's a couple of capacitors. We look up in the top right here, you can see these guys are looking a bit tarnished. Might be problems there. You can see why sometimes these can be long-term problems that you just, you know, who knows if those caps are okay. They're still on the board. They haven't fallen off in the ultrasonic or anything. So, you know, they're not too bad, but you can see we've got some tarnishing here and there. But, you know, that looks all right, I think. You know, that's not awful. If we look to some other areas, let's come up to Allsys Power Good here. And this one has some other stories. Again, you can see we've got some tarnishing on some of those resistors, center screen now. But all in all, it doesn't look too bad. Yeah, all in all, we're looking in good shape here. You know, again, there's a few tarnished components here and there, but nothing I think is screamingly awful. You can find stuff that doesn't look stellar in any laptop. So, like, yeah, all things considered, that is really clean. So what I'm going to do, I'm going to plug in the DC board, and I'm just going to see if it turns on. I forgot to put the DC board in the ultrasonic, so I'll just give that a light toothbrushing. There's nothing screamingly wrong with this guy. We'd be particularly looking for corrosion on this guy here. That's the sleep sensor. If this guy gets messed up, and we're right on the edge of the laptop here, so it very commonly does, but if that gets messed up, the laptop won't be able to detect if the lid is opened or closed, and that will prevent it turning on. I'm just going to get the alcohol as well. Not going to put on the cooler quite yet. If we see signs of life, then it's worth putting on. May as well clean this up as well. And one last area that we want to check is clean as well is the JTAG connector here. This is a diagnostic port. Again, right on the edge at the back of the laptop. This has a lot of mission critical signals going to it. If that guy gets messed up, again, that can stop the laptop from running, and this guy was messed up. There's lots of areas that I kind of wanted to point out and go, oh, that looks bad, but there were so many of them that it didn't really, there wasn't really a lot of point in going through all of them. There was just so many problems on the board. Actually, let's just plug in the fan as well, because that's the quickest way of knowing that it's turned on. Alright, power meter's up. Let's see what happens. Green light. Orange light. No fan spin. We had a little pulse of power, which was probably just inrush, and now it's just sitting at like 16 milliamps, which is basically nothing. Okay. So let's just do some very quick stabbing and just see if it's doing anything whatsoever. So put my black probe on a screw hole, and let's just check PP bus G3 hot. 2.7 volts. Okay, so that's low. That should be 8.6. So that's probably a short circuit pulling it down. PP3V42, we have a green light on the charger, so that should be fine. And it is. Alright, so we've got PP3V42. PP bus G3 hot is low, so let's disconnect that. And we're going to go up to resistance mode, and we're just going to check the resistance on that rail. $10 megohms. Well, that's not shorted. What about the other side of that fuse? About the same. And just to make sure, yeah, the fuse is intact. I've been punked by weird fuses before, so I'm paranoid about them. Alright, so PP bus G3 hot is not shorted, but it's also not going high either. So, where would we start with that? I guess what we could do is remove the fuse and then see if it goes high, because that tells us if something in the system is dragging it down or if the rail isn't powering up in the first place. So I think that's what I'm going to do, because that just tells that immediately just isolates, is this a supply problem or a draw problem? So let's just get my hot plate, and I'm just going to take this fuse off of the board. I'll put some fresh solder on each side of the fuse, and then I can probably soldering iron hero this guy. Surprisingly tricksy, that fuse, because it's on quite a heavy power plane in the board, so it puts up a lot more of a fight than you think it's going to. So let's check our measurements on both sides. So on the output side, we're seeing kilo ohms and rising. That's a lot lower than the megohms we had before, but it is rising. That's probably just capacitors charging up, so I'll give that the benefit of the doubt. And on the supply side, we were seeing just very high voltage, very high resistance there. Okay, so we'll power up the board again now, and we'll see if we should find that the supply side comes up to running voltage. And we get 3.2. So it is a supply issue. Okay, so I'll unplug this a sec. Let's open up the schematics for the PP bus G3 hot power supply. Let's have a look at how that works. Right, so here is our P-bus supply and battery charger circuit. This is page 50 of the schematics for reference. And as you can see, at the output, we have PP bus G3 hot. So this whole page, this is generating our main power rail. We've just removed F7140, which is our main output fuse. So we've isolated the system from the supply, and with the system isolated, the supply is only getting to about 3 volts instead of the 8.6 volts that it should be getting to. So we know that there is a problem on this page somewhere. So what's this doing? Let's start in the top left. In the top left, we have from adapter. So we've got the MagSafe connector coming in with charger voltage. It goes into the inrush limiter, which is this pair of MOSFETs here. Most motherboards, MacBook or otherwise, have some input MOSFETs that just allow the input power to be switched on and off, and so on. This means that the control chip down here, this ISL chip, that can control whether the input supply is on or off, and it can control that on both sides. So once we've gone through the inrush limiter, we're going to come down here, we're going to go through a current sense resistor here, and that current sense resistor, that's a very low value resistor, 0.02 ohms. And that has got 2 sense lines that go back to the control chip. And as the voltage goes through this current sense resistor, there will be a slight drop in the voltage because there's a little bit of resistance there. So the voltage at the output will be ever so slightly lower. And by measuring how much the voltage drops across that resistor, the chip can measure how much current is being drawn. So that means that the chip knows how much power the laptop is drawing from the charger. So we go through there. We've got some filter capacitors here, and then we go into a dual MOSFET package. And this is a buck regulator. So this dual MOSFET package, we've got a high side and a low side. The high side connects to the source power, the low side connects down to ground. And the control chip is going to pulse the high side and low side one after the other. It will bring in a pulse of charger voltage, and then when this switches off, this one switches on. So that pulse goes into the coil and it charges up the coil a little bit, and then it switches off. This guy cuts in and we have a ground connection to the left side of the coil, a positive at the output, and the coil releases its power and it goes through into the system. And by just pulsing the power on and off at very high speed, we get a high voltage to low voltage conversion done. That's a very flying overview of a buck regulator. So other stuff we've got going on this page as well, we do also have the battery charger down here. So the battery charger, we've got another MOSFET here, which connects up to the battery line. And this is bidirectional. If this MOSFET is engaged, we're either supplying charge voltage to it, or if there's no power up here, we can also engage this and receive power from the battery straight out to PP-bus G3 hot as well. And once again, you can see we have another current sense resistor here, so the system is also monitoring power going in and out of the battery. So this area here is also in play because remember, we've removed this fuse, so everything from the fuse to the left is in play right now. So what we want to do is we want to plug this thing in and we want to see if power is getting, we want to see if the correct amount of power is at least getting to the current sense resistor. Are we even getting charger voltage into this regulator? So let's have a look at that. So we need to find R7120. So because I'm using Flex Board View here, I can right click on stuff and it will cross-link it in both directions. So if I just right click on R7120 there, it will highlight it back on the board view for me. Makes it really quick to find stuff. I can also just Control F if I'm using the free version, but one of the perks of the paid for version. So R7120, it's up there. Let's have a look at that on the board. Right, so black probe on ground, and we're going to check that resistor there. And we've got 19.5 volts. And that's about correct. That's the amount of power I'm sending into this. An actual MagSafe charger will actually be a bit lower than this, but I'm using a Type-C power supply here. We're getting approximately just shy of 20 volts in, and these boards don't mind that. You have quite a big margin of error for these. So power is getting up to that resistor. What's next? So next in line after our current sense resistor, we go straight into Q7130, which is the dual MOSFET package. So this guy, I don't think there's going to be a problem with this guy because the two likely outcomes we would have is the failure modes that we're likely to see is that one of these MOSFETs has shorted through. So that might mean if the high side shorts through, then we would have charger voltage, so like 20 volts, would be going straight through this guy and straight out of the inductor. And we would expect to see the PP-bus G3 hot is at like 20 volts. And we would also probably find that this guy would immediately burn out and explode. That's not happening, so we've no reason to believe that there's a problem with the high side. So what about the low side? If this guy gets stuck on, then it's going to pull everything down to ground. And again, we've no reason to believe that that's happening either, because if that was happening, we would be getting no output here at all, because this guy would just be stuck pulling everything down to ground. Not only would we have no voltage, but we quite likely would see a low resistance to ground on PP-bus G3 hot. And if you remember, we actually had high resistance. So we've no reason to believe that either of these guys have problems. So without even needing to test that, we can probably look elsewhere. And the other thing we've got is U7100, the controller chip itself. So, well, where's that on the board? So we're looking at this area of the board right now. We've got our current sense resistor was there, our dual MOSFET package is there, and if we flip the board over, U7100 is this guy. And this is actually one of the guys where we saw a lot of tarnished components. So let's take a closer look at that. So this is a Intersil ISL 6259, which is a very, very common failure point on these boards. It's a well-known chip, this guy. And if you have a look at some of the components above it, if I just tilt the board just to change the light, you can see that some of those guys are pretty badly tarnished and they don't look super good. So this chip itself may have failed altogether, or it might be getting bad feedback. We did look at another MacBook Air not that long ago where one of the other controller chips was having problems with the components around it. There was a bit of corrosion that was causing it to get just bad feedback and not be able to measure what it was doing properly. The same thing might be going on here. Most of the resistors, the black guys, most of these resistors look okay, but these capacitors don't look too hot. So a dodgy capacitor could be causing us problems, or the chip itself may have failed. Remember, we cleaned this guy up pretty good with the Ultrasonic, but that doesn't mean that it's not stone dead. That might also be our issue. So I guess we could try measuring these. Let's at least look at what some of these lines are, and let's just see if we can make some stabs in the dark at this. So let's see. The first things of note are, I think, these two data lines coming in. I think that is current sense. Let's take a look at the schematic again. So here's our guy, and pin 28 and 27 are along the top row. We're basically going to check all of these top rows, and there's a couple of guys down the side that I want to check because those are going to tarnished components. So pin 28 and 27, 28 and 27. If we check the schematic, I'll just search for that. Next. There we go. So pin 28 and 27. There we go. So pin 28 and 27, those two lines come up here, and that goes to our current sense resistor. And there's a capacitor across these wires here, which is one of our tarnished boys. Now, if this capacitor goes short circuit, then that could be causing a bad reading across this current sense resistor, meaning that the chip no longer knows how much power is being drawn, and that would cause it to not function properly. So let's just quickly check the round trip for this current sense line. We have a 10 ohm resistor here, a 10 ohm resistor here, 0.02 there, and then we go back to the chip. So if we were to measure the resistance across these two wires here, we should see just over 20 ohms of resistance on this round trip. If we see something like 0, then that would indicate that this guy's probably shorted. So let's just go into resistance mode on the multimeter, and let's just have a look at what our round trip resistance is. Check these two probe points here. And we've got 20 ohms there, so that's probably not our issue in that case. As bad as that guy looks, it's probably not our issue. What's going on with these two guys here? There are those guys as well. That looks like capacitor C7122 and 7121. Those are going down to ground. So if either of these guys were short-circuited, well, let's just check a ground point and just check that. I can't see a world where this is our problem, but I'll put my black probe on ground and we'll just check both of these probes again and just check that we're not seeing low resistance. So that's high resistance there. That's high resistance there. So again, these guys, they don't look so hot, but they're not causing a problem. So what about this guy, these two guys here? They also look a bit dodgy. What pins are those? So that is 26, 25, and 23. So 26, 25, and 23. So 26, charger S gate. That goes up to our inrush limiter. Now, we're getting voltage to the current sense resistor. So we know that the inrush limiter is switching on. So that means that, you know, this resistor up here, this stuff, that's all going to be fine. We're getting past this. So I don't think that's our issue at all. So let's drop down to 25. So charge boot. So charger boot. This guy connects to the output. So this is a boot strap. And it's also connecting to pin 23, which is one of the feedback lines. It's not, well, I say one of the feedback lines. That's the phase line. So it's just checking directly the output from the transistors. And yeah, again, looks a bit tarnished, but I can't see that being our issue. We've got no short circuits in that area. We already know this. So again, we've kind of got no reason to believe there's a problem with these without just taking components off the board. So I'm going to move on. What about this guy down here? This looks like possibly another current sense line, I think. So those pins down there, that is pins 18 and 17. So this is battery current sense, I think. 18 and 17. Yeah, this is battery current sensing. So we could check this as well. We have no battery connected, but if there was a fault on these lines and the chip thought that there was a high power draw through this resistor, that could cause an issue. So again, we've got a 2.2 ohm, 0 ohm, and a 0.01 ohm up there. So we're expecting to see approximately 2.2 ohms of resistance on the round trip. So let's check 18 to 17. And we've got about 3.5 ohms. That's a little bit higher than I'm expecting. However, we're also going to have some losses in my probing, and we are looking at low resistances here. It's not a dead short circuit, and it's not sky high. So I don't think that's our problem either. So at this point, it seems more likely that this chip is just dead, and I'm kind of thinking that I'm just going to swap it out with a spare. So what I think I'm going to do is I'm just going to remove that and replace it with a donor board, and I'm going to try my luck on that. So we're going to start by removing the ISL 6259, and I'm going to go with, we're not doing full windscreen wiper here. There's a technique known as the windscreen wiper technique, and that would be that we just replace everything on the screen. Because at that point we go, we don't care, if we're going to start replacing the components, we'll just replace the entire circuit, and that way, whatever it is, we fixed it. And I'm not going full windscreen wiper, but I am going to change anything that's tarnished, because if I bring in a donor board here, so ignore the splatter marks on this where there's bits of flux all over it, but as you can see, all of the capacitors on this one, none of them are tarnished. They all look good. So basically, I'm going to swap out anything that's tarnished here. So basically, these capacitors, there's this guy down here that looks really dodgy as well. So we're just going to replace a whole bunch of those with the ones from our donor here as well, just in case. And, you know, I don't think they're the problem, but since we're going to do rework, let's just take the whole lot off. So I'm going to start by just drowning the area in flux. We're just going to take off anything that looks a bit crap, basically. Anything that looks a bit Jamie Oliver. Bleh. All right. Okay, here comes the hot air. I'm going to blow half of that flux away immediately, but no, whatever. Use more flux, everyone says. All right. You want flux? I'll give you a flux. Warming the general area up. That'll do, I think. Right, now we're going to come in with the soldering iron, and we're just going to just flow some fresh solder in and clean up those pads. And then that way, when I start bringing in the new components, we can just drop straight onto the board. We need some more flux in there, but we're going to wick it all down in a sec. I'm just trying to get solder onto all of the test points, just to tin those up. There we go. All right. Lots of flux, because we're going to start wicking. All right, let's get that big old blob first. There we go. Right, now we'll clean that up and suddenly it'll start making sense. Right, there is our cleaned site. Now I just want to quickly double check if I knocked off any extra components there, because when you come in with a big wick and a big soldering iron head like I just did, it's very easy to just pull up some extra stuff in the wick. And I think I might have gotten someone in the bottom left there, so I'm just going to double check. Yeah, I did. I picked up that resistor as well. So yeah, it's important to check, because you might just grab an extra component that you didn't intend to with the wick. And that's fine, because we've got replacements. The important thing is that you realise when you've done that, because yeah, I've made that mistake more than once. Cool. All right, so I'm going to start hot airing stuff across. Don't worry, we'll have flux down in a minute. Need flux down now. Alright, that'll do. I know it looks like I've ruined everything, but we do need some actual solder there. Okay, right. So we're doing all of our support components first, so I'm coming in at low airflow. And I'm just going to start picking off of the top board. Damn it. I dropped the first component. Great start. Okay, good news is we can just use the other one. Right, so we've got all of our parts back on the board now. So now I'm just going to touch up some of the joints. You can see that the joints around the ISL chip are not very good. And there's a couple of blobs on some of the other components that I just want to touch on as well. So more flux onto the board. And we're just going to try and run the iron all around the edges of the chip and just touch everything and just neaten it up a little bit. And then when we wash the board, then it will all look a lot tidier. So let's just try and get into those edges there. Yeah, it hasn't come out as a work of art, but, you know, this is my first time actually reflowing this whole area properly. So let's try that and see if it's good enough. Right, here goes, everyone. Fan spin. It's working! Right, that power cycle is normal. Okay, I'm powering it off. It's going to work, but we need a heatsink on it. Okay, let's go again, everyone. Pow. Watch it just not work now. Fan spin. As you can see from the power meter, we're drawing real amounts of power. There's our power cycle. It might do that 2 times before it starts, maybe 3. There's the second. And that's the real start. So now, if we go down to voltage mode, we'll just quickly measure PP bus G3 hot. And as you can see, that's now sitting at 8.6 volts. And you can see from the power draw of the laptop that it's now actually sitting at a constant draw. So that's actually started up now, and that's going to settle on the boot screen because there's no SSD in. But we're now in a position where we can actually plug it all in and see if the laptop will run. So what I'm going to do now, I've left the chassis over there. There's a couple of watermarks in the chassis. I'm going to wipe that down and I'm going to reassemble it, and then we'll try it in the chassis and see if we get a picture from the board as well. Right, we're all reassembled. So just a quick side note: while I was cleaning the inside of the chassis, I just wiped that down with a damp cloth. It was just wiping off just schmutz and stuff like that. But also, I did take the battery out and just inspect around the trackpad as well. There was nothing to see there, but because there was a lot of liquid damage under the logic board, it was important to check there because corrosion around the trackpad and things like that can also cause problems for the laptop. It's unlikely to prevent it from turning on, but you might get issues such as high fan speed or the trackpad or keyboard not working and things like that. So, the other thing to keep in mind as well is we're expecting the battery to be stone dead because there's been power issues on the laptop. So, let's just see how it responds. I'll plug in the charger. All right, we've got fan spin again. We should get a chime. It's power cycling. There's our chime. There's our Apple logo. And that means we're booting up. So in addition to that, you can see that we're now drawing nearly an amp. So the battery is actually charging now as well. We'll probably see that slowly start veering upwards because the battery will need to get going. Apple laptops, their typical behavior is to start at a lower charge current and then increase up to until it feels right. So we'll probably see that current increase, although it's dropped down to about 500 milliamps. That seems very low to me. It says the battery is charging, so, you know, we'll give it some time. But basically at this point, I'm just going to keep an eye on the battery, and if it looks like the battery is knackered or it's not holding a charge, then this would need a replacement battery as well. And going back to the conversation we had earlier on about, you know, whether it's worth fixing and stuff like that, if it turned out that the battery also needed replacing, you know, that's another 40 or 50 quid for a battery. So we've got to start taking that into consideration as well. So that's something that we might need to think about, but that's not really important to this video at this point. For now, we seem to have won. So I will do some monitoring on this. What I'm going to do is I'll put the back cover on, and I'm just going to leave it plugged in, on charge, and just switched on, and just keep an eye on it. See if it cuts out, see if it's charging the battery properly, and so on. And if everything looks okay, then at that point, I'm going to call the customer and try and sell them the repair that I've just performed, and hope that they take me up on my offer. So, and if they say no, then I shall take off the fuse again. Past that, we're finished. So thank you very much, everyone, for tuning in. We had a very, very bad looking board there, but an ultrasonic clean and then a replacement ISL chip to fix PP Bus G3 Hot has gotten this thing going again. Thank you, everyone, for tuning in. I'll see you next time. Bye for now.